question 2. So you don't have to draw a picture of it. I'm going to draw a picture of it because it's going to help when I explain stuff. F1, X1. Okay, between the masses I've got a spring. K1, K2, K3, I have a damper, C1, C2, C3, and I've got a damper here as well, which is C5, and I have a damper here as well. So I've got a multiple degree of freedom system. Okay, this could be, like I said, you could be looking at say an engine or something where there's dampers and engine mounts and lots of degrees of freedom, and you can set it up, you can represent it using this sort of linear method. Okay, so some complicated system with 3 degrees of freedom, and like I said, you can represent it like this using sort of lumped math methodologies. Okay. And the question is, obtain the equations of motion. Okay, I've said using the TVR method. I'm actually going to go through the full Lagrange's method just as an example to show you. And so it's quite clear that my T, my kinetic energy, is going to be the energies of mass 1, mass 2 and mass 3. So we've got obviously 1/2 m1 x1 dot squared, okay, plus 1/2 m2 x2 dot squared plus 1/2 m3 x3 dot squared. That's straightforward. There's no other kinetic energies other than the things in the mass. Like I said, you've got to take the energy of the whole system. So we're not dealing with 1, 2 and 3 separately. You've got to write them all out together. Now V is a bit more complicated. We're neglecting gravity, but we've got lots of springs. And so we've got 1/2 K1. Well, K1 is only associated with the motion of x1, so it's going to be x1 squared. But K2 is related to the relative motion of x1 and x2. So x1 minus x2 squared, that's K2. And then obviously you've got 1/2 K3, again the relative motion of x2 and x3. Okay, and R, which is our damping, this becomes quite complicated indeed, because we've got lots of dampers. C1 is only related to the velocity of x1, so it's x1 dot squared. 1/2 C2, relative velocity of mass 1 and mass 2, so it's going to be x1 dot minus x2 dot squared. C3, it's going to be x2 minus x3 dot squared plus 1/2 C4, well that's only related to x2, plus 1/2 C5, that's related to x1 and x3, so x1 dot minus x3 dot squared. So if I call this equation 1, This one I'm going to call equation 2, and this one I'm going to call equation 3, just to make life easier. If I take equation 2, I'm going to multiply out v. So v equals 1/2 k1 x1 squared plus 1/2 k2 x1 squared minus k2 x1 x2 plus 1/2 k2 x2 squared okay. And I thought the double pendulum had enough subscripts in. So all I've done in this line is basically multiplied out these terms here. Okay. So obviously x1 minus x2 squared becomes x2 squared, sorry, x1 squared minus 2 times k2 x1 x2, and obviously 2 times a half is 1, and then plus x2 squared, because you've got minus times a minus becomes a plus. So my L is t minus v. So L is t minus v, there's my t term, and there's my minus v term. Obviously all these pluses become a minus, okay? So that's minus, 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 minus. And all those minuses, this one and this one, become pluses. Those two terms there. Okay, and then we go through the process. So we're dealing with x1 to start with. Okay, so we have dl over dx1 dot. Well, there's only one term in the whole equation that's got an x1 dot in it. It's this one here. And obviously that becomes m1 x1 dot d over dt of that term becomes m1 x1 double dot. This is a bit more complicated because there are a number of terms with x1 in. We've got this one, and this one. So we have minus k1 x1 minus k2 x1, and then this one becomes plus k2 x2. What I'm going to do is I'm going to deal with R in a minute. We'll deal with x2 now. Taking derivatives is a lot easier when we haven't got sines and cosines. Okay, simple differentiation. Now if there were no dampers in this system, then obviously this would be enough to get the equations of motion, but there are dampers. Okay, so those are like I said, those are the enough to get three equations of motion if there was no dampers. Okay, because we dealt with this term and this term, or this term and this term, and if there was no damping, then R would be 0, and you just use those two terms to get the equation of motion. Okay. But the thing is, there are dampers, so I've got to deal with R. I can't avoid it. Okay, and so I've got to, with R, I want to multiply it out. Okay, so I'm going to write out R here. So if I put R here, then you can see it. Okay, I'm multiplying this term, this equation out. Let's move it up. So R, we've got 1/2 C1 x1 dot squared. Then it's this term plus 1/2 C2 x1 dot squared minus C2 x1 dot x2 dot. Okay, plus 1/2 C2 x2 dot squared. That's the second term. The third term, similarly, 1/2 C3 x2 dot squared minus C3 x2 dot x3 dot plus 1/2 C3 x3 dot squared. That's that second term. And the last term, C5. I have to deal with x1 dot, x2 dot, and x3 dot. So dr dx1 dot, well, there's this term. So I've got c1 x1 dot. this one plus C2 x1 dot. I've got this term minus C2 x2 dot. Okay, and there's then I've got this one down here plus C5 x1 dot, and this one here minus C5 x3 dot. That's x1, x2, dot. That's this term. This one plus C2 x2 dot. This one plus C3 x2 dot minus C3 x3 dot plus C4 x2 dot. Yep. And then lastly, with x3 dot, no, 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 yes, yes, no, no, yes, and yes. Okay, so to get the first equation of motion, x1, okay, it's these terms. And so, F1, okay, we've got this term first, m1, x1 double dot, okay, minus this term, but I'm going to do this term first. So this is plus, okay. Now in terms of x1s, I've got this one, and this one. So it's going to be C1 plus C2 plus C5, x1 dot, okay. Then I've got the x2 and x3 in here, so minus C2 x2 dot minus C5 x3 dot, okay. And then I've got this term in here, I've got x1 here, but it's minus, so this becomes a plus. So plus k1 plus k2 x1, then minus this term, minus k2 x2. So for F2, or for x2, again I've got this term up here. Okay, this one up here. And then I've got my C term, so again I'm going to group them together. So plus, in terms of x2 I've got C2, C3, and C4. And I've got minus C2 x1 dot and minus C3 x3 dot. And then in terms of my spring over here, this again becomes a minus, so we've got minus, or plus, sorry, we've got K2 and K3, minus K2 x1 minus K3 x3. And then for F3, or X3, I've got M3, X3, double dot. Again, looking at the C terms, I've got, in terms of X3, I've got C3 plus C5. Minus C5 X1 dot minus C3 X2 dot. And then we've got this term over here. This can be plus K3 X3 minus K3 X2. And the way I've written these equations means that I can write them in matrix form. Yes? Does indeed. Thank you. Thank you. So, in matrix form, we've got M1, M2, M3. Minus C2. So, by taking those three equations, You can actually write them in matrix form because they're linear. Okay, and these matrices are exactly what you find using the quick method. If we go back to the diagram and fold this over, my mass matrix is simply my three masses times by their accelerations. Okay, so M1, M2, M3 in a diagonal matrix. My damping, okay, well, I've got, if I take mass 1, it's the number of dampers, it's the sum of the dampers connecting mass 1 to either ground or to another mass. So we've got C1, C2 and C5. C1 plus C2 plus C5. I made a mistake, it seems. Where's my damping gone? Yes, C5 in there. So there was a mistake. I've written C5 here, look, sorry, there. But when I transferred it, I wrote C3. So that's the change I've made just there. If you wrote it down as C3, you're wrong, it's C5. This is why it's worth checking with the quick method. Okay. So you wrote C1 plus C2 plus C5, well that's what I've got there, okay. The second diagonal, I'll take the second mass, it's the sum of the dampers connecting mass 2 to either another mass or to ground. Well, I've got C2 plus C3 plus C4, which is connecting it to ground. C2 plus C3 plus C4. And then here, I've got C3 and C5 connecting mass 3 to ground or to another mass, so C3 plus C5. The off diagonals, it's the dampers between the masses. Well, for mass 1, I've got a damper between mass 1 and mass 2, so I've got a minus C2 here. And there's also a damper between mass 1 and mass 3, so I've got a minus C5 here. Okay. For mass 2, or sorry, between 2 and 1, obviously I've got minus C2, so that's just opposite there. And between mass 2 and mass 3, so this is this box, I've got a damper of C3, so that's over here, minus C3. And then obviously for the third, between mass 3 and mass 2, I've got minus C3. And between mass 2 and mass 3 and mass 1, I've got minus C5. And then obviously that's the dampers connecting mass 3 to ground to another mass. That's multiplied by my velocities. And then if I fold this over, we can deal with the springs. Springs connecting mass 1 to either ground or to another mass, K1 plus K2. K1 plus K2. For mass 2, it's K2 plus K3. And for mass 3, it's simply K3. Between mass 1 and mass 2, I've got a spring, minus K2, minus K2. And between mass 3 and mass 4, mass 2 and mass 3, I've got minus K3 in those two terms. There's no spring connecting mass 1 and mass 3, hence 0 and 0. Times by my displacements equal the forces. Okay, so like I said, it's quite, with such a problem, it's much quicker to use the quick method to get those matrices. But I'm just demonstrating the process of Lagrange's equations going through and solving for all of this lot here. So we start out, we work out TV and R, which are up there. Come on. TV and R, okay. It's straightforward looking at the equations. Simply T is kinetic energy, 1/2 mv squared. V is potential energy. Here we've got springs, so we're just doing with the springs. And R is just if you've got dampers. I work out what L is, okay, which is simply T minus V. And then from here I work out dl over, well, I do the partial derivatives and the time derivatives necessary to get the first and second terms of Lagrange's equations. I then dealt with R, because R also had lots of these relative velocities squared. So I've dealt with that on this page, okay, to get this equation for R, and then work out each of those things for the last term in Lagrange's equation, dr over dx dot, and then I plug them in, and I get these three equations here, which you can write in matrix form there, okay.